Hi, my name is Missy Epps, and I'm speaking tonight on behalf of myself and my colleague Russ Chianini for the 2020 Kirk Bryan Award Lecture. By the end of this lecture tonight, I want you to really believe that our community of geomorphologists and soil scientists need to adopt a new conceptual framework for how we understand mechanical weathering in Earth and even on other planets. So let's first think about what mechanical weathering is. I'd like you to imagine your favorite rock. Is it a big cliff or an outcrop, or maybe it's the tiny pebble sitting on your desk? And I can guarantee you that in every single one of those rocks that every single one of you is imagining, there is a crack, a linear void, a fracture at some scale or another. And mechanical weathering is the growth and propagation of all of those fractures over time. Mechanical weathering is crack growth. I don't think you can actually overstate the importance of mechanical weathering to Earth as we know it as human beings. The fracture of rock has a profound effect on everything from the formation of soils and sediment to the evolution of human life, and even to the atmosphere, to the composition of our atmosphere. And so it stands to reason that if we want to understand any chemical or physical or biological process on Earth or near Earth's surface, we must understand mechanical weathering. So here's the traditional view of mechanical weathering. We take a solid mass and we break it into smaller and smaller pieces. And the way that that breaking occurs is through some type of external stress forcing. Something like freeze-thaw or salt shattering or unloading. And in this case, Jackie Frost is exerting a stress level on the rock that's higher than level X in order to break the rock. So what is that magic stress level X that we need to break up rock? Well, in most geomorphology literature and weathering literature, it's exemplified by something called the critical strength of the material, something like the tensile strength or the compressive strength, whereby once you've exceeded that stress level, fractures will propagate critically, that is, very rapidly and unstably, and the material fails. Okay, so now let's see how this traditional view holds up when we go out in the field and we actually start observing real Earth surface processes. Some of you may have already seen this video from Twain Harte, California. This was from the summer of 2014 when we actually observed a true critical cracking event. It was really amazing. And you'll watch it here as it goes on, but shortly after this event, my colleague Bryan from the U.S. Geological Survey went out to this dome and he instrumented it with rock bolts. And with these instrumented rock bolts, he could actually measure the stresses in the dome day in and day out. And then, as luck would have it, 2 years later, there was another critical cracking event, just like the one that you saw in the video. And it led to this pop-up of granite that you can see in this image. Now remember, the critical strength of granite is around 5 to 20 megapascals. Guess what the stresses were that Bryan measured out in the field? On the order of 55 kilopascals, almost an order of magnitude less than what would be required to break the rock if you were trying to get to the stress level of the critical strength. So clearly we're missing something. Something is not right in our conceptual foundation for how we understand this fracture. And it was conundrums like this and other ones that really led me away from geomorphology and into fracture mechanics literature to try to understand what I was missing. And it turns out I really didn't need to go any further than my own house. There's been a crack in my wall growing for almost 10 years since we did some remodeling back in the early 2000s. And so this is similar to cracks that might grow in your windshield over the course of a week or a month. And it's that slow, steady crack growth that comprises an entirely different kind of cracking than critical cracking. And we in fact call this subcritical cracking. It's the slow, steady crack growth over time at stresses that are orders of magnitude lower than the stresses required for critical explosive fracture like what you saw at Twain Hard. So once I understood what subcritical cracking was, I started diving into the geomorphology literature to see if I could find any reference to it. And others had invoked subcritical cracking in their own work. But none of us in the geomorphology community had come out and explicitly said, look, all mechanical weathering must be dominated by subcritical cracking processes. And that's what Russ and I set out to do in our 2017 paper. So recognizing that mechanical weathering is driven by subcritical cracking processes has all sorts of really interesting implications for understanding Earth surface processes. But the biggest one, I think, is that it opens the door to a new link between climate and mechanical weathering that we really never considered before. Material scientists have long understood that subcritical cracking is driven by chemophysical processes that are happening right at the crack tip, and they're enabled by the stresses that are getting exerted there. And so because subcritical cracking is a chemophysical process, bond-breaking process, then the rates and nature of that cracking depend on the environment at the crack tip. And so if that's the case, and mechanical weathering is subcritical cracking, then mechanical weathering necessarily must depend on climate in a way that is completely independent from climate's influences on stresses. So Russ and I demonstrated how this might work in a real setting through a numerical model. And we modeled subcritical cracking rates in granites as a function of the average annual relative humidity that might be experienced by those granites. And each of the black lines that you see in this graph represent an isopascal, if you will, a line of unique stress loading magnitude. And so you can see that if your rock is sitting in a relatively humid climate, it's going to crack at rates that are almost 2 orders of magnitude greater, faster, than if it's sitting in a low humidity environment. And so this was nice evidence through numerical modeling that subcritical cracking is climate dependent, independent of stress. Okay, so now we have a new view then of mechanical weathering, where climate can influence mechanical weathering through its influences on stresses, but it can also influence mechanical weathering through its influence on crack tip processes. And this is what Russ and I laid out in our 2017 paper. But what does it mean? Can we actually go into the field and demonstrate these concepts in real life settings? Okay, so first let's ask ourselves, are the cracks that we see out in the field, regardless of where they are, growing subcritically or critically? Are most cracks growing like the Twain Hard Dome, or are they growing like the crack in my wall? Well, we first went out to do this in the Blue Ridge Mountains of Virginia, where we looked at 20 outcrops that were made up of 4 different rock types, and all those outcrops were found in a very small area, so they shared a similar climate, vegetation, and relief. In other words, they shared a similar stress history over time. And then with my colleague Greg Hancock, we went to those outcrops and we measured their long-term erosion rates using beryllium-10. And we reasoned that if the cracks that were growing in those rocks were leading to their erosion, if those cracks were growing critically, then the erosion rates should most correlate with the critical material properties that we could measure in the rocks. But if they had been growing subcritically, then there should be stronger correlations between the subcritical parameters that we could measure in the lab and the erosion rates that we measured in the field. And so here are those data. So each dot, it represents an average of erosion rate as well as the material properties for each of the 4 rock types that we measured in the field and in the lab. And you can see that the subcritical cracking parameters in the bottom 2 graphs much more strongly correlate with erosion rates than the critical cracking parameters in the upper 2 graphs. And so this and some other data that we presented in this paper was some of the first field evidence to really suggest and support the idea that the vast majority of mechanical weathering that we observe in rock and bedrock and outcrops is subcritical in nature. Okay, so that data really helped us to understand that long-term mechanical weathering is likely subcritical in nature. But how can we show that it's also climate dependent? To do that, we need to actually observe cracking as is happening. And then we need to be able to isolate the influence of stresses on that cracking and see if there's any climate dependence left over. And so we did this by taking 2 granite boulders and sitting them out in the sun in humid, temperate North Carolina and semi-arid New Mexico. And we got about 4 years of data. And what we did is we instrumented each of the boulders with little acoustic emission sensors that could actually listen to the rocks as they were cracking. And at the same time, we measured the atmospheric conditions with an adjacent weather station. So importantly for these data sets, over the years, my colleagues and students have analyzed them, and we have a strong understanding of the stresses that were driving the cracking that we observed, namely freeze-thaw and thermal cycling. So for this analysis, we removed the freezing days from the data set in order to just have a single type of stress that the boulders experienced, and that related to thermal cycling stresses. And so what that allows us to do is use a single variable, in this case the rate of temperature change, as a proxy for the thermal stress magnitudes experienced by the rocks. And so here's a graph of all 4 years of data plotting cracking rate as a function of that thermal stress proxy. And you can see, in fact, that there's a very strong correlation between rate of temperature change and cracking rate in both data sets. Okay, so now that we've seen how climate's influence on stresses is reflected in the cracking rate that we observe in the data sets, we now want to see if we can isolate climate's influence on cracking separate from climate's influence on those stresses. So these graphs are showing you the observed cracking rate that we measured in acoustic emissions per hour as a heat map. And so if you take any one little square like this one on the graph, what it's telling you is the cracking rate that we measured for all times where the vapor pressures were what's indicated and the stress levels were what's indicated by the y-axis. And so the way to read these graphs then is that if climate in the form of vapor pressure or temperature is controlling the cracking rates independent of stresses, then we should see cracking rates increase for every single one of these rows on the graph that represent different levels of stress as a function of rate of temperature change. And that is in fact exactly what we see. The relationships are not as strong for temperature, but they're very strong and consistent for vapor pressure. So in these data, we find that cracking accelerates under hotter and wetter conditions, even when stresses are held constant. So the data you've been seeing so far is some of the first field data of its kind to support this new conceptual framework for understanding mechanical weathering, that is, climate-dependent subcritical cracking. And understanding mechanical weathering in this way has all sorts of interesting, exciting avenues of exploration that we could take. For example, if you think back to our friend Jackie, we know that she can exert some of the highest stresses on rock in terms of environment, both subcritical and even perhaps critical. But at the same time, because she's acting under cold conditions, the rates of cracking that are occurring due to her processes could be quite low. And so this is for future workers to figure out. But in the meantime, what if we go back to our Twain-Hart problem and conundrum? So namely, how can we get critical cracking in granite when the stresses that that granite is experiencing are only 55 kilopascals? Well, we can find answers in thinking about subcritical cracking. And what you have to understand is that the stresses that matter for subcritical cracking are actually the stresses that are found right at the crack tip. And the magnitude of those stresses is directly proportional to and driven by how long the crack is. So as the cracks are growing, even if stresses are staying the same and staying very low, the crack can accelerate because the stress that's being felt right at the crack tip is increasing. So at Twain-Hart, it turns out that there were cracks growing subcritically between 2014, when you saw the critical event in the video, to 2016 that we're talking about now. And so here's the image of where the crack tip was in July of 2015, and you can see that between then and September of 2015, it actually grew off of the image. So that by June of 2016, when the critical cracking had occurred, we may have had no more additional external stress loading, but the crack was long enough that the stress intensity at the crack tip caused the critical event. And not only that, but the week of 2016 where this critical cracking event occurred, Twain Harte experienced some of its hottest temperatures on record and much higher than normal vapor pressures. So, in fact, climate may have been exerting an influence on that critical cracking event that was above and beyond the influence that it had on the stresses that drove it. Okay, so what's next? My colleagues and I have started exploring these ideas in some of the driest, coldest places on Earth in Beacon Valley, Antarctica. And not only that, we've also started to try to understand how cracking may evolve over very long geologic timescales by looking at cracks forming in boulders on alluvial fans of different ages in Owens Valley, California. And we hope that all of this work related to climate-dependent subcritical cracking will help us to not only better understand mechanical weathering as a whole, but also help us to understand the overall role that weathering has played in Earth's history so that we can better predict the role that weathering may play in Earth's future, both in landscape evolution and even the change of Earth's own climate.